Hello, dear students. Very hearty welcome to Ask IITians. My name is Rahul Bisla, and I'm going to be your maths teacher. And first of all, many congratulations to all of you for clearing your 10th grade. And now some of you might be having a bit of anxiety, bit of curiosity, like how the 11th grade is going to be. Is it going to be bit challenging, difficult, or it's going to be easy or interesting or boring or whatever. So there will be a lot of things going on in your mind. Let me just clarify you right there. The 11th grade maths and 12th grade maths, or basically the JE curriculum, it's going to be very interesting for all of you. So this will definitely help you enhance your curiosity. It will help you with having more understanding. It will help you with critical thinking, right? And it will definitely improve your logical reasoning. So I'll request you to be a bit patient. Yes, initially you might feel a little bit challenging, but yeah, just be patient, be regular, right? Do your practice as well as revision on the regular basis. Definitely, I'm promising you, definitely you're going to excel in the 11th and 12th grade and the exam, whatever you'll be appearing for, let it be JEE Main or JEE Advanced, along with your boards, right? So I'm very excited to start this journey with you. And I wish you all the best for choosing Ask IITians. And yeah, definitely we're going to do the best for you guys. And I ensure that you are going to love this decision of yours that yes, you have chosen Ask IITians to prepare for this exam. So without further ado, let's start the 11th grade syllabus. And I'll tell you a little bit about 11th grade syllabus. There is going to be a good mix of algebra and geometry and trigonometry. Yes, I know trigonometry, some people are scared from the 10th grade. But yeah, so one thing I will be requesting you, whenever there is going to be a chapter started from 11th grade, so I would want you to revise the topics of the 10th grade, the prerequisites that will be requiring in 11th grade. So if you do that, definitely you're going to excel the 11th and 12th grade, and definitely you're going to master all the concepts in this one. Right. So without further wasting their time, I'll be starting the first chapter of 11th grade, and I hope you can see my screen, right? So the first chapter that we'll be dealing with is sets. The name is written in front of you, sets. This is going to be our very first chapter for the 11th grade. Now, I'll be asking you whether you have heard of this term sets in your real life. You might be recalling this. Yes, you heard it. Set of 11th grade material, set of physics books, or a set of denims, or maybe a set of umbrellas. Yes, so I do understand that you might have heard this word in the day-to-day life also. So this is going to be our first point of discussion, like what is a set with respect to maths. So now we'll be discussing how this word means in the domain of maths, right? So this is what will be challenging, and so we'll be starting with this. Firstly, you can see an image in front of you. You might be seeing some stationary items on the left side. Then on the top right side, you can see jelly, apple jelly, some crunchy peanut butter, some another jam is there, right? So the objects that you normally eat or edible things are there. Then in the bottom right side, you can see a bunch of books there, Flight in Darkness, something like that, right? So definitely you can see here the first one, these are all your stationary items. These are all your stationary items, right? As it's written in the image also. These are your edible items, things that you eat. These are your books. So these are a combination of a particular kind of objects, right? So that's exactly what the definition of a set is. So when we'll be writing the definition of set, a well-defined collection, a well-defined collection of objects is known as a set, right? So a well-defined object collection. The most important word in this whole definition is well-defined. This is going to be highly important for us that we understand what is the meaning of this well-defined, right? Now, I'll just give you one view, like how you can see whether something is well-defined or not. If the list stays the same for you, your friends, your parents, and everyone else, then it's going to be a well-defined collection. Let's say if I ask you what is the list of all the prime ministers of India till today. Definitely, whatever list you will be giving, same list will be given by your parents, your friends, and everyone. Let's say if I ask you the list of best actors in India, definitely you might be having a different preference. Your sister might be having different preference. Your parents might be liking someone else. That list for sure is not going to be same for everyone else. So that's when we can say that this list is not well defined. So I hope you are having some idea. The first thing, right? The collection of vowels in English alphabets. You can see that the collection of all the vowels, if we talk about, right? Vowels, are A, E, I, O, U. So I'll just write it here. A, E, I, O, U. These are the members of the set. These are the vowels that we have. So if you ask anyone, you ask your friend, anyone, if you ask, they will be giving you the same alphabets. Maybe someone might write E, A, I, U, O, or some other rearrangement might be there, but they can't take any other alphabet than these when they'll be asked about vowels. So this is going to be fixed for everyone in the world. So hence this is a set. This collection is known as a set. So now if we talk about the next one, the collection of first five prime natural numbers. First prime natural numbers. You know the first prime natural number is 2. Please don't start with 1. 1 is neither prime nor composite, right? Second is 3, then 5, then 7, then 9, no, then 11. So these are the first 5 prime natural numbers that we are having. So if you ask anyone in the world, they will be giving the same answer. Hence, this is a set. This collection is a set. Now we are having this collection in front of us. The collection of good cricket players of India. If you are interested in cricket, so you might be knowing the first image is of MS Dhoni, second Virat Kohli, third Rahul, KS Rahul, and fourth is everyone knows Yuvraj Singh, the hitter of six sixes in an hour. So these might be my best cricketers. Some of you might be saying, sir, where is Bumrah? Right? Some of you might be saying, sir, where is Sachin? Right? So that list might vary with everyone. So definitely the list of good cricket players of India. This is not a set. This is not a set here. You can see this is not a set. Similarly, if I talk about the collection of difficult topics in mathematics, you might have had some interactions with your seniors, your elder siblings. You might have asking which topic of 11th grade is going to be difficult. They might have given different list of chapters. Someone might have told you integration is going to be very difficult. Vectors are going to be very difficult. Others might say other chapters. Someone might feel trigonometry is very difficult. Someone might feel complex number is difficult. So this list is not fixed for everyone. Hence, this is not a set. This is also these collections are also not a set. So I hope the understanding of set is clear. When the list is well defined and it's going to be same for everyone, it will be a set. If it might vary with different people, then it's not a set. Right. So now very quickly we'll just revisit this. Vowels is a collection of vowels is a set. Collection of first prime natural numbers is a set. Good players, good cricket players, not a set. And difficult topics in mathematics, this is not a set. Right? So let's move forward and let's see integers whose squares are less than 20. Is this a set or no? If you ask integers whose squares are less than 20, so firstly we'll think of numbers which are perfect square and less than 20. Definitely I can see here 16, right? But 16 is a square of 4 also and minus 4 also. Next square number less than 20 that you can think of is 9. 9 is a square of 3. 9 is a square of minus 3 also. Now we can think of 4. 4 is a square of 2. 4 is a square of 2 and 4 is a square of minus 2 also. Next, 1 which is a square of plus 1 and 1 which is a square of minus 1. That's also there. Next, 0. Can we include 0? Shall we? I think yes, because 0 is also an integer. So the question is asking the integers whose square are less than 20. So 0 is a square of 0. So definitely then asking about the integers whose squares are less than 20. So definitely I can tell you that plus minus 4, plus minus 3, plus minus 2, plus minus 1 and 0. These are the integers. These are the integers in total which whose square will be less than 20, right? If I take plus 5, 25, minus 5, 25. If you go on either side of plus and minus 5, definitely their square will be greater than 20, but we need less than 20. So these will be there. How many do we have here? 2 plus 2, 4 plus 2, 6 plus 2, 8 plus 1, 9. So there are total 9 such integers. There are 9 such integers whose square is less than 20, right? So this we understood. This is a well-defined collection, plus 4, minus 4, plus 4, minus 3, plus minus 2, plus minus 1, and 0. If you ask anyone in the world that uh, list the numbers or list the integers whose squares are less than 20, everyone will give you the same answer. Someone might start it with 0, someone will start it with 4, as we have done here, right? Order might vary, but the listing will be same, right? So now let's move on to the notation part, how we notate this. So yeah, a set is denoted by capital letters. Set is denoted by capital letters. This is one thing that we should be taking care of, denoted by capital letters. Now, small letters, A, B, C, D, X, Y, Z, something, something. So the members of the set are denoted by small alphabets. Members of the set are denoted by small alphabet. Right. So if let's say if I have to write here, A is an element of set A. If I have to write that this A element is set of element A, what does this mean? That I am trying to say that A belongs to, sorry, the small A, the member of the set, small A belongs to the set A. Mathematically, how we'll be writing this? We'll be writing this mathematically as A belongs to A. This is the symbol. This is the symbol for belongs to. I'll just write it here. This is the symbol of belongs to. Right? So I hope we're sorted till here. Now we'll be moving to the next part. What if any element is not belonging there? Like I can say here, 3 belongs to this set. So if I say this collection, this set as some set A, so I can say 4 belongs to A, 4 belongs to A, or 3 belongs to A, but 5 does not belong to this set. 5 does not belong to this set. So how we write when an element doesn't belong to this? We'll write this as A belongs to A, and we'll strike this. We'll just strike this, that this doesn't belong to. So this symbol, and when we strike this, this will mean doesn't belong to. Doesn't belong to. Right? So if I have to write here that 5 doesn't belong to this, so I will be writing this as 5 doesn't belong to A. Right? So I hope we are clear till here. We'll be moving on to the next set. Next feature of a set. Next part we'll be moving on to order. As I already told you, someone might be writing A, E, I, O, U. Someone might be writing U, O, I, E, A, or someone might be writing any random order also. So the order of elements does not matter. Order of elements doesn't matter. Right? Next part, repetition. If I write this A 3 times, A, E, I, O, U, something like this. So even if you repeat this, so it will not be any different than the initial set that we were having, A, E, I, O, U, right? Because what exactly we'll be telling when we read this, like this set contains A, this set contains I, this set contains O, this set contains U. So in short, the elements are same. So as many times we'll be writing, the repetition doesn't matter. So repetition doesn't make a difference. Doesn't make a difference. Right? So I think this is also sorted. Now we'll be moving on to the next part. So now we are getting the complete definition of set, mathematically defined set. What is going to be a set? A well-defined object collection. This word we have already seen, a well-defined collection of distinct objects. Why we are saying distinct? Because we don't uh, prefer the repetition. We don't include the repetition. Wherein ordering of objects is relevant. We have discussed that also, like you write it in the reverse order or whatever order you write, the ordering will not matter. So you can write it in any order, right? As long as there are distinct elements and there's a well-defined collection, we will call it a set, right? Chalo, let's move on to the next part. There are some important sets or very common sets. There are some very common sets, and we'll be discussing about their notation. Very common sets are there, and we'll be discussing about their notations. The set of natural numbers. You have studied this from 7th grade, 8th grade, and up to 10th grade, you have studied natural numbers. So this is natural number. So if I'm saying ki x is a natural number, I'll be writing this as x belongs to this n, capital N. Whole numbers. Whole numbers we denote by W. So let's say if I have to say x is a whole number, so I'll be saying x belong to the set of whole numbers. Next, Z. Please don't make this mistake. We all know that this is from the word Jalen. And whenever we'll be saying that x is an integer, so we'll be writing x belongs to Z. Please don't write x belongs to I. This doesn't make any sense. The set of integers is not denoted by I. The set of integers is denoted by Z. All right. Next, moving on to next set. Very famous, very important set for us, rational numbers. That is denoted by Q. You know, Q is the short of quotient. We know quotient. So whenever I'll be saying X is a rational number, I'll be saying X belongs to Q. Right. Next, real numbers. Real numbers for the first chapter of 10th grade. I hope you all enjoyed finding the HCF LCM and solving those easy questions, right? So yes, if X is a real number, we'll be writing this as X belongs to R. X belongs to R, right? So these are some of the very important, most common sets that we'll be using throughout the 11th and 12th grade. Now we have understood what a set is. We have seen some of most common sets. We have understood how we'll be writing the elements of the set. We have understood how we'll be writing the name of the set itself. Now we'll be seeing how we can represent a set. You might have seen here that we've used curly brackets here. Yes, I didn't explain that part, but now we'll be getting into depth of that, like how we'll be representing this set. So there are basically two ways how we represent the sets. We represent the sets using the roster form or tabular form. Like in this, we'll be writing this as a list. Just give me a second. In this, we'll be writing this as a list of elements. And in the set builder notation, we will be writing this with the help of a rule or a formula or a generic way of like how we can write the elements. So one by one, we'll be getting to these. First one we are starting is roster or tabular notation. As I told you, we'll be writing it as a list. So let's just read that definition once again. Here the set is described by listing. We'll be listing each member of the set separated by commas. This is very important. We'll be separating the elements by commas within curly braces. So if we talk about the set of integers less than 20, the question that we have done, if I have to write that set, so I can write, because sets are denoted by capital letters, so I'll write it as A, curly bracket, we'll start with -4, -3, -2, -1. You can see I'm separating all the elements by comma. 0, 1, 2, 3, and 4. And I am again closing the curly braces. So in the left side and the right side, we'll be having curly braces. We'll be writing the elements and they will be separated by the commas. So this representation or this notation we call as the roster notation or tabular notation. All right. So I hope you understood this. Now it's time for us to write the tabular notation or the roster form for these set of all real numbers strictly lying between 0 and 0 0.5. 0 and 0 0.5. So I hope you understand. Here this you can see this is 0, this you can see 0 0.5. So definitely in between here there is going to be a number 0 0.25. Definitely there will be 0 0.1 in between. So let's say if I'm saying real numbers, because reals can have rational, irrational, decimals, everything, right? So let's say I'm calling this as a set A. So I can write the elements as 0 0.1, 0 0.2, 0 0.22, 0 0.25, 0 0.23, or let's say 0 0.3 only, and so on. You can see there are going to be infinite elements in this set, because we are very well aware that there are infinite rational numbers or between any two rational numbers, and there are infinite irrational numbers between any two rational numbers. So definitely this list is going to be infinite. So we can't list all the elements. We can write some of the elements. Then we can use this dot 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 three dot notation we can use to signify that the list continues on and on, right? So just make a note of this very quickly. All right. We have some more examples to deal with. So we are given set of all the letters in the word proportion. We are given the word proportion. So if I write that, you can see there are some repetitions. This O is coming twice, not just twice. O is coming thrice. Are we going to write it three times? No, right? Because we've studied this, like we'll not be repeating it and the order will not be mattering. So I'll just write it here. P R O P O R T I O N. So I hope you can see O is repeated three times, R is repeated twice, P is repeated twice. So if I have to write only that, I have to form a set with the letters of the word proportion. So I'll be writing this as a set A, and I'll be writing only the unique entries, that is P, R, O, T, I, and N. So this is what I will be writing. I hope you understand. We'll not be writing O three times and we'll not be writing R two times, or will not be writing P two times. So this is how we can make a set. All right. We have some more examples here. Set of all even natural numbers. So if I have to form a set using this, I hope you understand. Like, can I say 0 is a natural number? No. So 2 will be starting with the smallest natural number, which is 2, 4, 6, 8, so on. This list will never end. You will be having thousand, million, billion, and then again the next even number. So this will never stop. This will never end. And these kind of sets, yes, we'll be coming back to this. These kind of sets are known as infinite sets, where the number of elements are infinite. Next, set of integers with absolute value at most 2. Absolute value, I hope you guys remember it from the 7th grade. Absolute value was like you have to just take the magnitude, not the sign. Not the sign. So if I someone gives you absolute value of 7, that will be 7. Absolute value of -7, that will be 7. So you will be ignoring the sign, you'll be just taking the magnitude. So yeah, if I point it here, if you take magnitude of 3, that will be 3. At most means maximum value that it can attain is 2. So 3 can't be there. So 2 we have to take. Integers only. First, another thing that you take care of is integers. So we'll be taking 0. 0 is an integer. Absolute value 0. Less than 2. 1 we can take. Absolute value is going to be 1. So I'm writing alongside. 0 we can take. 1 we can take. -1 we can take. Right? 2 also we can take, because the absolute value of 2. And yes, we can go till 2. Right? We can take -2 also. -2 will also be there, and we'll be enclosing these within curly braces. You can see all of these are separated by comma. We'll call this as any set. Let's say you want to call this as set X. You can call it set X. We've been using A for some time, so I don't want you to guys make some understanding that all the sets are written as A. No, that's not the case. You can use any capital letter to denote the set. All right. So till now we are sorted with this kind of presentation or this notation, which is roster form or tabular form. Moving on to the next. Next is set builder notation. Set builder notation. What is that? Here a set is described by specifying the characterizing properties of its elements. So we will be looking at the properties that will be shown by each and every element. For example, we have seen this example above also, and same thing is written here. The set of all even natural numbers, all even natural numbers. So I have written this as like 2, 4, 6, 8, dot, dot, dot. This, and this was your tabular form, right? Or roster form. This was your roster form. But this time in set builder form, we have to write this with the help of the property that elements are describing. So I hope, do you remember how we were writing the odd numbers previously? Every odd number will be a multiple of 2. I hope you remember that fact. So 2 into anything, right? So we'll be having this as A equals to all those x, such that you have to use the colon here. You have to put the colon here. X such that x equal to 2 into n, where this time you will be putting the semicolon here. You will be putting the semicolon here, such that this n that you are involving is a natural number. So yeah, you can input different natural numbers. You can put n as 1, you'll be getting 2 into 1 as 2. You can put n as 2, 2 into 2 will be 4, n as 3, 2 into 3 will be 6. So this will also give you the same set, 2, 4, 6, and so on. But we can write it in a compact form. So, or I can say that set builder notation is the notation where we can write the set in compact form, right? Another way that we use is instead of using this colon, sometimes we use a vertical bar like X, curly braces will be forming X such that is denoted by this vertical bar also. X such that X equal to 2n, rest will be same semicolon. This n is a natural number. This you should be recalling now. Capital N natural number, capital W whole number, Z integers, Q rational numbers, R real numbers, right? So this is how you can write a set in the set builder form, right? So there's a definition that we should be looking at. In other words, a variable x, let's say we have taken the variable x as you have taken here, denoting each element of the set. You can see with the help of this rule, with this result, x equal to 2n, I have represented all the elements of this set, right? Is written inside the curly braces, and then after putting a colon, the common property, we have put a colon here, you can see here, this is the common property x equal to 2n, right? Denoted by px, possessed by each element of the set x of the set is written within braces. So how we can write this? If we follow these definitions, you can say A is a collection of all those x such that this x belongs to this property P of x. This is how we can write it, right? Like we were having x equal to 2n there. So this is how we can denote the elements in the set builder form. All right, so same thing is written here, x such that P of x holds, or x, this vertical bar also means such that P of x holds, which is read as the set of all x such that P of x is satisfied, which we have written in the form of x belongs to P of x. All right, now we have some examples in front of us and we will be writing these in the set builder form. Firstly, I will be asking you to stop the video here and then try all of these three on your own. Take 30 seconds for each case and try this. I'll not be stopping. I will be moving forward. So yeah, the set E, they have given the name of the set. So this time I will be writing the set as E and all positive multiples of 3. Positive multiples of 3 means I will be having 3, 3 to the 6, 3 to the 9, 3 4 the 12, and so on. These are the positive multiples of 3 that we are having, right? So how this is the roster form. This is the roster form. Can we write it in the set builder form also? Yes, we can write it as. So that will be E equals to all those x such that x, now this x is going to be a multiple of 3 and positive multiple of 3. So I hope you understand 3 into 1, 3 into 2, 3 into 3, 3 into 4. So in short, we'll be having 3 into any number k where this k is a natural number, right? I hope this is clear to you guys. Moving on to the next question. A is 1, 2, 3, 4, 5, 6, 7, 8. Now they have given you a roster form. They have given you the roster form already. And you have to make the set builder form from here. Not roster. Just the roster. Roster form is given to you and you will have to make the set builder form from here. Right? So what's the one thing that you can observe from here? 1, 2, 3, 4, 5, 6, 7, 8. These are counting numbers. Yes, we remember these are counting numbers. And another thing is counting number means natural numbers, but they are either I can say less than 9 or I can say equal to 8. So the way that we can write is x is A is the set of all those x such that x belongs to, or firstly I can write x is less than 9 such that x is a natural number. This is something we can have, or another way of writing this will be x where x is less than equal to 8 and x belongs to the set of natural numbers. So these are the ways how you can denote a set in the poster form. Right? Next, you have to write the set of reciprocals of natural numbers. We know the natural numbers are 1, 2, 3, 4, 5. So the set that we'll be having is 1, 1 by 1, the reciprocal, 1 by 2, 1 by 3, 1 by 4, and so on. This list is never ending because the number of natural numbers are infinite, right? So this is your roster form. Roster form. If you have to write this in the set builder form, we'll be writing this as x such that x equal to 1 by n. This n can take the value as 1, this n can take the value as 2, n can take the value as 3, any value that you can think of, and such that, or where n belongs to the set of natural numbers. So this is how we can write the set of all the reciprocals of natural numbers. Right. So till now we have a good clarity about what sets are, how we write the members of the sets, how we write the name of the set, what are the way of representing a set. We have studied two methods. First is roster method. Second is your set builder method. Right. Let's move to the next part where we'll be studying the types of sets. There are different of types of sets that we'll be studying in this one. Right. So different types of sets we'll be having here. I have given you just the pictorial representation of that contains the name of all the sets. Like we'll be studying about empty set, we'll be studying about singleton set, we'll be studying about equivalent sets, equal sets, infinite set, finite set. All these things we'll be studying, right, one by one. Let's start with the first one, that is empty set. I hope the name itself is giving very clear indication that it's going to be empty. There is going to be nothing in that set. So another name of empty set is, you can see here, another name is null set or void set. These names also you can find in the question. Like there is a null set, or there is a void set, or there is an empty set. So we'll say a set is said to be null set or void set or empty set if it doesn't contain any element. It doesn't contain any element. Right. Next is the denotion, how we denote empty set. An empty set is denoted by phi. I hope some of you might have seen this. Some of you, this might be new for some of you. So this phi, phi, this is also a Greek symbol, just like your alpha, beta, gamma, theta. So you will not have to worry about this. So we denote the empty set by phi. Right. A set consisting of at least one element. If there is at least one element in the set, one thing is for sure, that that set is not empty. So we'll say A is not empty, or we can call this as A is not equal to phi. Right? I'll give you one more way how we denote the empty set. We just write the curly braces and we don't put anything inside this. Means like there was a set, yes, but because that's empty, there is no element inside it. So if just empty, just the curly braces given to you, that also denotes the empty set. All right. So now we're moving ahead. So this is given to us as mathematically set A is empty only when X belongs to A is not true. This should not be true for any element X. There should not be any element X. There should not be any element X that belongs to this set A. Right? Or I'm saying is X should not belong to A. Next, A equal to phi if and only if there does not exist any X such that X belongs to that. Same thing. Just the way of writing is different. A is equal to phi if this. All right, we are getting a new symbol here. This reverse E. I think you might be seeing it the first time. This is for there exist. We read this as there exist. And if we strike this, we'll be calling as doesn't exist. There doesn't exist. Right? So we'll be having A is a null set or phi if there doesn't exist any X such that X belongs to A. So there is no X which belongs to A. Right? So we're given some examples. Set of even prime numbers less than 2. No, there is no other prime number less than 2. So we'll say this set is going to be a null set, phi set. Set of natural numbers strictly between 5 and 6. Natural numbers are 4, 5, 6, something like that. Yes, there are some before also, but between 5 and 6, there is no natural number. If let's say they have been asking about natural numbers between 4 and 6, yes, 5 is a natural number between 4 and 6. Right? So between 5 and 6, there is no such number. Hence, we'll be saying this set is a null set, void set, or this is 5. Try the last one quickly. Try the last one quickly. Set of reals whose square is equal to minus 2. All right. So real number. So if I real number means positive, negative, rational, irrational, anything you can take. So if I take 0 square, that is going to be 0. If I take plus 2 square, that is going to be 4. If I take minus 2 square, that is going to be plus 4 again. If I take root 3 square, that is also going to be 3 plus 3. If I take minus root 3 square, that is also going to be plus 3. So I am not finding any number, any real number whose square is coming out as negative. That means the square of real number can't be negative. I hope you already know this. So set of reals whose square is equal to minus 2. Minus 2 is a negative number. Can't happen. Not possible. Let's say A is a set phi. All right. Next, moving on to the next type of set, that is singleton set. Again, very, very clear from the name itself. Singleton. Singleton means single, right? There is going to be only one element. A set consisting of a single element is called a singleton set. All right. So mathematically, if we say how we represent the singleton set, this is going to be A is a singleton set only when there exists a single element X such that X belongs to A. Only one element should be belonging to A. If X belongs to A, there should not be any other element. Y should not belong to A. No other element should belong to A. Only one element should be belonging to the set A. All right. Then only we can say this. A is a singleton element if, okay, you might be saying, sir, this is some typo, spelling error. No, IFF. This is also very important for you. This we read as if and only if. If and only if. And this reverse E, this I told you just before this, there exists. There exists. So if I read this, so mathematicians have introduced a lot of symbols to make our job easy so that we'll not have to write these long statements. We can just say A is a singleton set if and only if there exists exactly one X. Exactly one is the important term here. Exactly one. So this is very important. Exactly one X such that X belongs to A. Only one element should be belonging here. Right, next set of all natural numbers whose square is equal to 9. We know the square of minus 3 is also 9. We know the square of 3 is also 9. But mind it, they're saying natural numbers. So only 3 square is equal to 9. Hence, this is a singleton set because when I'll be writing this set, we'll be having only 3 in that. Only 3 as a single element there. Next, set of all positive integral roots of the equation x square minus 2x minus 15 equal to 0. So I hope you guys are all very well familiar with the middle term splitting part, right? You have studied this in 9th grade polynomials chapter, 10th grade polynomials also, 10th grade quadratic also. So middle term splitting we can use in this topic. And when we factorize this, we'll be having x square minus 5x plus 3x minus 15 equal to 0. When we rearrange these terms, we'll be getting x minus 5 into x plus 3 equal to 0. This will give us the value of x as plus 5 and minus 3. But we are looking for, please pay attention on this word, positive integral roots. We are looking for only the positive integral roots. So this will be accepted, this will be rejected. So only one root of this equation is going to be a positive integral root. Hence, we'll say this will have single term or this is going to be a singleton set. Well, next, x belongs to real number if x minus 5 is 0. If x minus 5 is 0, you know, x is going to be 5. Only 5 is the value that if we input here, that can make this equation x minus 5 equal to 0. So yes, this is also a singleton set. All right. Moving on to the next, I hope void or null set is clear to you, singleton set is clear to you. Now moving on to the finite set. Again, it's very, very clear. See, the names are self-explanatory on their own. Finite set. A set is called a finite set if it has finite number of elements or countable number of elements. You can say this, countable number of elements. Right? For example, this is given to you x square minus 2x minus 15 equal to 0. The same equation that we'll having in the above case. So we'll be having this as x minus 5 into x plus 3 equal to 0. Positive integral roots again they're saying, so we'll be taking x equal to 5 here and this x equal to minus 3. We'll be rejecting. Okay, so x equal to 5 is the only thing we'll be having. So A set is having the element 5. You can see there is only one element. If you have like one element, 20 elements, 1,000 elements, 1 million elements, still that is going to be a finite set. If you have 1 trillion elements, still countable. We should not be saying there are infinite or never ending number of elements, right? So this is clear. So if I ask you finite set definition, so formally a set is said to be finite if it is either void set. I already mentioned if there are zero elements, still this is finite set. Or its elements can be listed, counted by natural numbers. Like we have one element, we have two elements, we have three elements, 20 elements, 50 elements, something like that. And this process of listing terminates at a certain natural numbers, like 1, 2, 3, 4, 5. Let's say we stopped after 1,000 key. Okay, there are 1,000 numbers or elements in this set. Right. Simply put, a set is finite if the number of elements is it contains is either zero, either it's going to be zero or equal to a fixed natural number. Then we'll say this set is a finite set. Right. We've seen some examples. Next, again, very clear from the name itself, infinite set. If someone asks us what is an infinite set, the set which is not finite is called an infinite set. Infinite set. Or we can say is where the counting of number never ends. If the counting of the number never ends, then we'll say this is an infinite set. All right. Moving on to the next part. Set of all integers strictly greater than minus 10. Strictly greater than minus 10 means minus 9 is greater than minus 10. Minus 8 is greater, minus 7, minus 6, minus 5, minus 4, so on. You'll get into the positive numbers like 2, 3, 4, 5, and so on. Again, you'll keep moving. This will never stop. The list is never ending. The list is never ending. That's why we'll say that this is a set which is infinite set. Right? So you can say a set for which the process of listing or counting of elements by natural number does not terminate. 1 million, then plus 1, then 1 billion, then extra, then 1 trillion, then it will keep going. It will never stop. That's why this is called an infinite set. Right? Simply put, a set is said to be infinite if the number of elements it contains is not equal to 0. This is not a void set, not a void set, or any fixed natural number. The number of elements is not a natural number also, fixed natural number also. Then also we'll say infinite set. All right. Now let's take the example of this set of all people in India. Right now, when I'm recording this, I think the population of India is 1.4 billion, somewhat around that. Right? We are the number one country in terms of population. Right? So, but still countable. The counting ends at a point. So, is this going to be a finite set or infinite set? This is going to be a finite set. Yes, it's a set which contains a large number of elements, but still finite. The counting is ending at a point. Next, x belongs to real numbers between 0 and 1. This is 0, this is 1. We already know there are infinite rational or irrational between any two rational numbers. So yes, this is going to be an infinite set, right? If you look at this equation, x belongs to integer and x square minus 5x plus 6 equal to 0. If we solve this using middle term splitting, we can simply write this as x minus 2 into x minus 3 equal to 0, right? I hope you can simply factorize this using the middle term splitting, right? So I'm doing this bit quickly. So x is going to be 2, x is going to be 3. There are only two integers. X belongs to integers. There are only two integers which are the roots of this equation or that can make it 0. Hence, we can say there are finite roots of this equation or finite integers that can make this 0. So this is going to be a finite set, right? Now, moving on to the next topic, which is cardinality of a set. Cardinality will be the number of elements that will be there in that set. So let A be a finite set. Firstly, cardinality is defined for a finite set only. Because if the set is infinite, we can't count the number of elements in that. Right? Then the measure of number of elements of A is called cardinality of A. We call this as cardinality. The number of elements, very important, number of elements of set A, we call as cardinality or order of A or cardinal number of A. So these are the three terms that we use. We either call it as cardinality, or we call this as order of the set A, or we call this as cardinal number, or we call this as cardinal number. So these are the three ways how we write the cardinality of a set, and we denote this by n of A, number of elements in set A, or we denote this by enclosing this within two vertical bars, that is mod of A, or order of A. O of A, this is order of A, right? This is how we'll be saying, this is how we'll be denoting the number of elements of that set, right? So next we'll be having is, thus if A is a finite set, A is a finite set containing m number of elements. Let's say there are m elements in that. So we'll be saying cardinality of A equals to, I'll say this as number of elements in A. Same we can write it as magnitude of A, or enclosing this within the vertical bars, or I can say this as order of A. All of these are going to be m. So m elements are going to be there in that set, right? So I hope everything that we discussed today is clear, and I hope you found these things super interesting and super easy. Yes, the first chapter is the easiest chapter of the whole 11th grade. But yeah, make sure to revise on time. Make sure to practice the questions that we'll be sharing, the DPP that we'll be sharing for this topic. If you stay regular, if you revise regularly, if you practice questions regularly, definitely you're going to excel your competitive exams as well as your board exam. All right, so that's it from me for today. I'll see you in the next session. Till then, take care. Bye bye.